Hello, welcome to the test review solutions for section 3.1 to 3.6. We're going to work the problems from page 235, but before we work those problems, I want to go ahead and talk about the test coming up. It covers sections 3.1 to 3.6. As far as Rolle's theorem goes, you need to know the definition, but with Rolle's theorem, you just set the derivative equal to 0, which is another way of saying find the critical point. So just know the definition, but I'm not going to ask you to work a problem because you'll be finding critical points throughout the test. The mean value theorem, you'd need to know the definition and also be able to work problems. So setting the derivative equal to the slope and solving for that point. And then the rest of it is what we've been doing the last few homeworks. Finding critical points, doing the first derivative test where you give me a maximum, a minimum, the increasing and decreasing intervals. And remember, when you give a max and a min, also need to find the y value by plugging the x value into the original equation. Then the second derivative test where we find the inflection point, the concave up and concave down intervals. And of course, you also need to get the y value of the inflection point by plugging into the original equation. Horizontal and vertical asymptotes, you need to be able to find those. And when you are telling me what the asymptote is, you need to do it in the form of a line equation. So y equals some constant or x equals some constant. So for the horizontal it would be y, and for the vertical it would be x equals some constant. Then do a rough sketch of the graph by looking over all of these things. When you found all of that, you will have two problems where you have to find everything and do a rough sketch. So those two problems are 16 points each, and that is the largest part of the test, those two problems. But then all the rest of the problems will be just finding max and min, finding inflection point, finding increasing, decreasing intervals. It'll just be kind of questions that ask about. You might have a couple of asymptote questions, but all of it, if you know how to do these two problems, then you're going to know how to do all these other problems. There are two multiple choice and true false, so that's fewer than the first two tests that we did for the semester. And that is just covering your notes, and really you just need to study your notes on Rolle's theorem and the mean value theorem to be able to answer those two questions. And just a hint here, if you have a complicated fraction, and you need to set that to equal to 0 to find the critical points or inflection points, you only need to set the top or the numerator equal to 0 to find where the function's equal to 0. And then if you need to find also where the function's undefined, if there is any spot where it's undefined, that's when you set the bottom or the denominator equal to 0. So you don't have to have this tremendously complicated fraction that you set equal to 0 and try to solve. Remember, it's really just about the top and the bottom separately. And if you want to remember what I'm talking about, just see number 29 on page 203 that we worked on the last homework in order to see what we had to do that. And you won't have a problem on the test that's as complicated as number 29 really, but if you know how to do number 29, then you are absolutely set up for success for anything that I could throw at you. All right, let's work these review problems. All right, we are on page 235 and doing number 8. So bringing that into view, we're going to find the points guaranteed by the mean value theorem, all right? And number 8 is f of x is equal to 1 over x. Okay, so we're going to first find the slope, and this would be the secant slope of the secant line. So, and our interval here is 1 to 4. So that would be f of 4 minus f of 1 over 4 minus 1. So that's 1/4 minus 1 over 3. That'd be negative 3/4 over 3. That's the same as negative 3/12, which is negative 1/4. So I'm going to rewrite f of x as x to the minus 1. So f prime of x would be minus x to the minus 2. So that's minus 1 over x squared, and we want to set that equal to the secant slope. Now you could cross multiply here, but this one's fairly simple, so I think you can just eyeball this, that our value c, where the slope of the tangent line is equal to the slope of the secant line, is going to be plus or minus 2. But negative 2 is outside the interval. Okay, so negative 2 is outside the interval. So 2 is the answer, only 2. If the interval included negative 2, we would have to put that. Okay. So you just got to be careful to get the slope right. The mean value theorem is not a particularly difficult problem. Okay, next one is number 17. Okay, so the instructions for 17 is to use the first derivative test and find any extrema. So a fancy way of saying maxes and mins. We have 1/4 t to the 4th minus 8t. Right, 4 times the 4th is 1, so that's t cubed minus 8. We're going to set that equal to 0. So our critical point occurs at t equals 2. Okay, so using that to find extrema. I have a 2 here, negative infinity, positive infinity. Let's plug in 0 to the left of 2. So that's going to be negative. Be negative 8, right? And how about 3? That'd be 27 minus 8. That's positive. So we don't have a maximum, but we do have a minimum. So our minimum occurs at the point 2, and let's plug 2 in. 2 to the 4th is 16, divided by 4 would be 4, minus 16, so that is negative 12. All right, so plug that back into the original. Don't accidentally plug it back into the derivative, or you'll just get 0. And there's no max on this. Now, just since we're here, let's go ahead and do the increasing and decreasing intervals. Decreasing from negative infinity to 2, and we are increasing from 2 to infinity. Didn't ask that, but that is good information. Okay, let's see if we can fit in number 19 here. So number 19, we want to find points of inflection. We have f of x is equal to x plus cosine x. And our endpoints are 0 to 2 pi. Otherwise, it would go on forever, wouldn't it? So to find inflection points, and we'll go ahead and find the concave up and concave down interval as well. But we have to get the second derivative. So the first derivative would be 1, and the derivative of cosine is minus sine. We don't have to set that equal to 0 because we're going and finding now the second derivative. And that's going to be derivative of sine is cosine. So minus cosine x, set that equal to 0. Well, on the unit circle, if you'll look at the unit circle, cosine x equal to 0 at pi over 2 and 3 pi over 2 within this interval between 0 to pi. So our inflection points occur at pi over 2, and then if we plug back into the original, it would be pi over 2 plus cosine of pi over 2, which is 0. So pi over 2, and 3 pi over 2. And then you plug 3 pi over 2, it would be 3 pi over 2 plus 0, so another 3 pi over 2. Those are your points of inflection. Just for practice sake, let's go ahead and find the concave up and concave down intervals here. So we've got 0, 2 pi, pi over 2, 3 pi over 2. All right, so 0 is part of the interval. I can actually go ahead and plug that in. So cosine of 0 is 1, so that would be -1. So we're concave down there. Pi would be a good one to pick. So negative, that'd be positive because it's -1. That's positive. So concave up. And then at 2 pi, it would be +1, so negative again, so concave down. So it didn't ask you to do that on the problem, just asked you for this. But it's good practice. And so there are the intervals. I won't write the intervals down, so it didn't ask that. Okay, that does it for 19. Let's move on to 25. 25, we want to find any horizontal or vertical asymptotes. So we have h of x is equal to 2x plus 3 over x minus 4. So you can't factor out the denominator here. This is pretty much, we can eyeball both of them. We have a vertical asymptote at x equals 4 because that makes the denominator 0. And we have a horizontal asymptote. We have a tie for the highest power. We have an x over x, but the coefficient would be 2 over 1, so at y equals 2. So this one was purely an eyeball situation. You really didn't have to do a lot of work on that. All right, 28, we have f of x is equal to 3x over the square root of x squared plus 2. All right, so do we have a vertical asymptote? Well, because you're squaring this x, there's no way to make that value negative. You would need it to get to -2, wouldn't you? But you're squaring it, it's no way to make it negative, so there's not a vertical asymptote. Now, horizontal asymptote, we have 3x over the square root of x squared. That's the same as 3x over x. So we have a horizontal asymptote at y equals 3. Now, there's actually one at y equals -3 as well, because you do have to take the limit as x approaches -infinity and put that negative out front. However, I am not going to give you one on the test where you have to worry about that. Okay, but just for future sake, if you were to graph this on your calculator, you would have a horizontal asymptote at y equals -3 also. But again, I don't want you to really worry about having to take the limit as x approaches -infinity as well. The ones that I give you on the test, you would be able to just report y equals 3. on that. So what that means is I'm not going to be giving you any on the test that have a radical to deal with for figuring out asymptotes. All right, so I probably shouldn't have assigned that problem, but it's good to go ahead because you might have, in college calculus, you might have to deal with that. All right, 33 and 41, we're going to do the entire kit and caboodle, all right, on these. So we have f of x is equal to 4x minus x squared. So that is a sad-faced parabola, right? That negative in front of the x squared term. It kind of helps to know what the shape looks like. That can help you get the right answer. So this is not a fraction here. So I'm going to go ahead and start writing things down. There's no horizontal asymptote. There's no vertical asymptote. So now let's do the first derivative test. It's going to be 4 minus 2x. Going to set that equal to 0. And we would have a critical point at x equals 2. So let's go ahead and write that down. I don't really care about the y value on the critical points, but I do want you to put that max min inflection point. Okay, so let's take a look at the increasing and decreasing intervals. Right, so we have 2 here, negative infinity and positive infinity. All right, let's pick 0. Put a 0 in, we're going to be positive. Let's pick 3, so that's going to be negative. So we are increasing until we get to 2, and decreasing, so we do have a maximum at 2. So we have a max at the point 2, plug 2 in, that's 8 minus 4. So at the point 2, 4, we have no minimum. We are increasing from negative infinity to 2 and decreasing from 2 to infinity. All right, you've piled up a lot of partial credit there already, and we haven't even gotten to the second derivative test here yet. All right, f double prime of x is just negative 2. That's always less than 0, so there's no inflection point. Because there's no x to solve for, this is always negative. So if you just got a constant, negative 2, always negative, so that means it's always concave down. So we are concave down from negative infinity to infinity. Concave up, none. Okay, we have gotten out of our 16 points, if this were a test problem, you've gotten 12 now. So our rough sketch, we're always concave down. I actually know this is a sad-faced parabola. I'm just going to plot the maximum at the point 2, 4. So let's say over 2, 4, something like this. We know it's always concave down. So just draw something like that. And there you go. Beautiful. Yeah, hopefully you'll get one that easy on the test. All right, they're not all super hard on the test. So you could have one like that, or maybe just a slightly more challenging than that one. Okay, let's do number 41. We need to do one that's got some asymptotes, right? That adds a little bit to the complexity. So here we have f of x is equal to x plus 1 over x minus 1. So I like to do the asymptotes first. We do have a horizontal asymptote. If you eyeball that, really the highest power is to the first power on both of those. The coefficients are 1, so at y equals 1. We also have a vertical asymptote at x equals 1. because that makes the denominator 0. Okay, let's do the first derivative test. I'm just going to go ahead and bite the bullet and do the quotient rule. So it's the bottom, x minus 1, times the derivative of the top, which is 1, minus the top, x plus 1, times the derivative of the bottom, which is 1. Important to put the parentheses around that. All over x minus 1, all squared. So cleaning that up, that's x minus x. So the x's go away. Negative 1 minus 1, that's negative 2 over x minus 1 all squared. Now, that's never going to be 0 because the top is a constant. However, we do have a critical point where the denominator is 0, and it's at that vertical asymptote, right? At x equals 1. So let's write that in and get some points. There's no y value there, but at x equals 1, we have a critical point. Now I'm going to do my sign line right here, because I kind of ran out of space there. Got a critical point at 1. I'm going to plug into here. The bottom's always going to be positive because no matter what number you put in, you're squaring it to make it positive. So a negative over a positive is negative. So this graph is always decreasing. And at 1, we have a vertical asymptote. So we have no max, no minimum. We are decreasing from negative infinity to 1, and also from 1 to infinity. Again, I can't put negative infinity to infinity because at 1 we have an asymptote. It's not decreasing there. The function doesn't even exist there. Okay, you've piled up a lot of nice points on this one. You didn't have to do a whole lot of thinking on it, even. Okay, so let's take a look at. Let's rewrite f prime of x as negative 2 times x minus 1 to the minus 2. So I rewrote it just so I could take the second derivative a little easier. If you wanted to do the quotient rule on that, you could, but it would be a little nastier than this. So negative 2 times negative 2 is 4 times x minus 1 to the minus 3 times the derivative of the block, which is 1. So that's 4 over x minus 1 cubed. Now that's never going to be 0, is it? However, I have a possible inflection point where the bottom is 0. So we have an inflection point at x equals 1. So at the asymptote, we have an inflection point. But there's no y value. If you plug 1 back into the original equation, you'd have 2 over 0, right? Which is undefined. So let's do our test for concavity. Inflection point at 1. There is a vertical asymptote there. Negative infinity. Infinity. Okay, to the left of 1, I'm going to pick 0. That'd be 4 over negative 1 cubed. 4 over negative 1, that's negative. So concave down. And then greater than 1 is 4 over a positive, so concave up. So concave down from negative infinity to 1, concave up, 1 to infinity. So we've achieved 12 of our 16 points. So now we need to give a good try on a rough sketch. And the asymptotes do confuse people sometimes, and you're not going to get a graphing calculator on the test. You can just use this type of calculator on the test, okay? So horizontal asymptote at y equals 1. So let's draw that in red. We have a vertical asymptote. I'll draw that in green. Vertical asymptote at x equals 1. So however you draw this graph, you cannot pierce the red or the green. So concave down, always decreasing. The only way you can draw this to not pierce the red or the green would be like that. And then over here, so that is concave down. Over here, it's going to have to be like that. That's concave up. Doesn't pierce either asymptote. All right, let me get this asymptote improved. There we go. All right, so this is a great problem as a test review, because we dealt with this kind of strange looking graph where you have the two completely different graphs. We have horizontal and vertical asymptotes to deal with. We rewrote the first derivative to make it easier to take the second derivative. That's great. That's a smart move doing that. Otherwise, you're going to have kind of a nastier looking fraction that you have to deal with. So there you go. So this is a pretty good test review. The previous homework assignment where we had 5 problems where we did in section 3.6, that was a fantastic test review as well. So this assignment plus the last assignment plus maybe a little bit from the mean value theorem, looking over that, would be great problems to rework for the test. All right, good luck on the test. That's all I've got for this video, and we will see you when I do the lecture for 3.7.